So we are going to continue our previous thing, how we could have inversion as well as the transformation, rather unitary transformation between two spaces. And at the end, whether it was a symmetry transformation or an inverse transformation, we had that was basically identified by a certain operator, which in turn was identified by a certain matrix transformation, which made some transformations invariant under some inversion. And the inversion may be the property, the space remains invariant, or the components which transform in that space, they become invariant. These are two ways of interpreting active and passive transformation. So in our today's class, what we are going to do is we are going to see make a sort of mnemonics or graphical way of trying to see these transformations, how we can see them, these orthogonal transformations, and in the symbolic way, how we can have, rather the appropriate title will be reversion and iteration of transformations. So we are going to somehow play with these transformations to the point where some of them can remain invariant or they may not remain invariant. They remain invariant after a series of transformations. So, but the transformations which will remain invariant have to pass. So they themselves have to pass through some orthogonal transformations, some transformations from given transformations. So, for example, in case of reverse transformation or converse transformation, so if phi inverse is a reversed or converse transformation, then sigma I is psi I, wait one sec. Sigma I is sigma I is sigma k phi of ki inverse. So this so you have a so this inverse transformation phi k inverse, which is having two indices. So if a transformation under inverse transformation or under reverse transformation will leave this operation invariant. So this inverse matrices or inverse transformation, it can be represented either as is equal to like this, permission of this, or reverse of this. So you have ik here, it's ki here. It's also known in the literature who say it, this is also called it as adjoint matrix of phi ik, which is denoted by symbol like this. Now the question is, now the following question can be asked. So if you have so we have a psi system which is given by this sigma transformation, and we have another transformation, tau system, and we have transformations there also, such that psi is written as psi of k is equivalent to sigma of I phi I k, and sigma is m tau of m omega mi. So if it's you can write this equation 1, 2, 3, 4. So you can see here, and further the direct transformation of psi system and tau system can be written as, so we have written psi as sigma phi of this, and this sigma we have written in terms of this tau. So we have written a transformation in psi transformation via this matrix transformation, and this sigma, this coefficient, it can be written in terms of tau. So we are writing psi in terms of tau. So it's a sort of how we can relate two transformations. So further, if you want to see sigma system, psi system, and tau system, we can write psi k as sigma I, sigma m. So here you see it's a sigma, its subscript is I, and here subscript is m. So you will have I and m. If you want to see this transformation, it goes like tau of m omega, so tau of m omega mi, and phi of ik. Phi of I, we just simply substituted this here. Substituted sigma, in presence of sigma we have this thing, and phi ik is as the same. So so you can again you see it will come out to be sigma tau of m. So now omega m, and so I will, this thing we can write it as chi of m k. So it's phi. So we have seen, so this I will be common, so we can this is repeated index, so we can write it like this. And chi of mk can be written as sigma of, now you see chi of mk, if we want to write it in terms of sigma, so chi of mk is equivalent to I omega mi phi I. Oh, yes, omega I k, yes. So chi m is written as, chi of m k is written as omega mi phi of I k. Chi of m k is written as wait one second. So how is chi of mk is written as chi of mk now you want to write this chi of mk is written, okay, you write it like this. So you have written psi in terms of tau, in this you can write it like this. That's fine. So if omega and if phi and omega are orthogonal, so is chi. So this follows that sigma of chi of nk star chi of nk star k I omega of phi of I k. So we will write it here. So if you have sigma chi of nk star is equal to sigma k sigma I. So chi you want to write it in terms of omega. Chi you want to write in terms of this omega mi phi of ik, and this nk also you want to write it in terms of phi, but we'll write it in terms of nl. That's it. Phi of lk star. So we can write it as if one of them is like this, we can change this to conjugate of this. That's it. So if you further write, so you can just keep them here, omega mi omega nl phi ik phi lk, kk is common, this is phi il. Phi il is, we can also write it as a delta function, delta il, or so if it's orthogonal, I is L, so it will be omega mi omega n so it's LL, it will be omega ni, so it will be basically again it will be delta, and II it will be delta n. So again what we have got is basically the thing is that expansion of psi k in the orthogonal set chi of ml mk, and iteration of two orthogonal set constitutes a new orthogonal expansion. So we have written sigma in terms of psi k and psi k in terms of this phi ik, and related the two. And in the sense, this relation we can further say, we can relate this chi first in terms of mi, then nli. We can relate these two transformations, two iterative transformations, and if they are orthogonal, so we can write the expansion of psi k in terms of orthogonal set. So this was the exercise. So the iteration of two orthogonal expansion is itself orthogonal expansion. So this is the thing. So this relation chi of chi of if you remember the relation chi of mk, this relation determines a new set of function given by the matrix multiplication of two this thing. So in this chi of mk, these phi and psi are somehow embedded. So that's it. And in the other case, so it's this is the embedding of two matrix sigma and phi I contained in the same thing. And if we want to write phi I in terms of omega ml, and phi ik in terms of this thing, and using reverse transformation we can write the relationship. Omega ml is this, and phi of lk can be written as this. So the whole point of this exercise is to show that we can write this entire thing. If we want to make a chart, if we want to make a chart out of it, how we can write it, that the iterative transformation of a given matrix can be written in terms of another matrix, and how we can come from one matrix to other and back to the same. So if you want to write it in terms of graphically, if you want to write it, if sigma is 1, tau and psi, this is phi, this is omega, this is chi. So you can go from this to this, and you can go from this to this, and you can go. So you can go from. So if you want to represent it by this diagram, this how you can write iterative transformation. You can always go from this to this, this to this. So if you want to write it diagrammatically, so trace of this tau of psi is basically, you can go from trace of n tau of sigma, cross of trace of sigma of psi. So you can go in terms of this matrix tau to psi, tau to psi. So if you want to go from tau to psi, it is the same as if you are going from this to this and this to this. So going from this to this, a transformation going from this to this, it is the same as if you are going from this to this transformation and then this transformation to this transformation. So you are arriving at a given transformation via these two transformations. It will lead you to the same result. Yes, yes. And the relations can be summarized as, if you want to summarize this entire thing or entire procedure, this can be summarized as psi of k can be written as sigma I phi I k is equivalent to m tau of m chi of m k is sigma of I sigma tau of m omega m I sigma of k psi of k phi of k I tau of m psi of k chi of k m sigma of I and yes. So chi of mk can be written as sigma of omega mi phi ik So it can be written as this, it can be written as this, and omega L can be written as and phi of ILK can be written as LM by LK. So you can see, so the question is, I'll write it. So in a triangle of transformations, we can choose the direction of transformation in such a way that we can choose so in a triangle of transformations we can choose the direction of transformations in such a way that a set of expansion coefficients of second can be expressed in terms of third. So you can see it from there. Tau of sigma. So sigma is common. So you can write it in terms of third. So these two can be expressed in terms of third. So this and this transformation can be expressed as if you are going tau goes to psi. So the expansion coefficient tau in terms of omega and sigma, the expansion phi, can be expressed as if tau goes to psi with these expansion coefficients. Now the point is, so this is the thing in the continuous case, and the reverse transformations can also be written in the so in the same sense there can be one is the homogeneous transformations, another is the heterogeneous transformations. So in the sense that once we normally talk of dimensions, we only talk of 1, 2 and 3, and if we talk of finite transformations, so if the transformations are in infinite dimensional space, so you can there is no problem. You are mapping the transformations, infinite dimensional transformations to the infinite dimensional transformations. But if we have to specify the dimensions, then you have to specify it's 2, 3, 4, the number. Then only these relations can hold for the heterogeneous case. So you have to specify if it is 2, 3 or 4. So if you this sort of diagrammatics for a 3, that expansion coefficient of the third can be expressed as the expansion coefficient of these two transformations. They get absorbed in the third one. So this can be, so if you have not only for heterogeneous transformations, for example, not homogeneous transformations, we can have the same sort of exercise here, in the sense that so if we choose we have a discrete so psi of x is written as sigma of I phi of x is equal to sigma of m tau of m chi of m x sigma of I tau of m omega mi psi of x phi I star x dx, and tau of m is psi of x chi of m star x is sigma of I omega im. This is reverse transformation. Now, so you have written psi in terms of sigma and sigma in terms of tau. and further psi tau and tau in terms of psi and phi, so you can write tau psi of chi m, so you can have this thing. So if you again, the way we have written it for homogeneous transformation, if you want to make a diagrammatics for it, for if you have sigma, this is psi, this is tau, this is rho, this is zeta, this is zeta prime, so this is omega, this is omega, this is eta, this is chi, so you can have it like this. This is new, yes, 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 this is so you can have tau goes to sigma, sigma goes to psi, psi goes to, so you can have this. This is sigma goes to tau, tau goes to sigma, this is inverse transformation. Tau goes to psi, so it is the same. If tau goes to psi means first tau goes to sigma, sigma goes to psi. Tau goes to psi through chi, but psi will come back to tau by chi inverse. This is inverse transformation. So you can go from tau to psi by a transformation through chi, this transformation. But if you want to come from psi to tau back, you have this inverse transformation. In the same way, you can see for psi to rho and rho to psi. Here psi and psi are inverse transformations. So this is a chart. This was for homogeneous transformations and this is for heterogeneous transformations. And the point is that how we can have these orthogonal transformations and whether they are homogeneous or heterogeneous, how we can see them. So if you want to for these again we can do the same exercise here also. The way we have done it for homogeneous transformations, we can do the same exercise here also, such that if phi of ik is equal to sigma, so the way we try to show it, if it's orthogonal in the previous one, we can do it for this thing also. If it's orthogonal, then and zeta k of L is equal to chi of k and eta L. So again, so we can write this here, V of IL as sigma phi of k zeta of KL. So in the previous one there were two transformations, sigma I, sigma M. Again, so now we can have sigma k, so this will be equal to sigma k, sigma M, sigma N. So omega I m, chi of M k, chi of K n, chi of K n, neta of NL. So it will be equivalent to sigma of M. So it will be equivalent to chi of M k, chi of K n will be delta of K n. So that's it. And the way we have chart out there, if you want to write it for homogeneous transformation, if you want to just see this, because here it's sigma, psi, rho and tau. Here it was tau and psi also, but we did it through this sigma. So, but for this thing, so if for two diagonal transformations, nu and chi. So this is one, this is chi, this is nu. So there are two diagonal transformations which are mediated, where omega im is sigma k phi I k chi of k m, and the diagonal transformation goes through k m phi of I k chi of k m neta ml. So it can be written as this trace of sigma rho, trace of the, sorry, trace, not trace, let's see, if this is sigma and this is rho, so this is sigma and so sigma and this thing can be written as, you are coming from trace of n sigma of psi plus trace of n psi of tau into trace of n tau of rho. Again, so if you have to come from this to this, it means that you are going from sigma to psi, then psi to tau, then psi to tau, then tau to sigma. So the path is bit inverted. So to go from this to this via some orthogonal transformations. So we have an orthogonal transformations with given symbols. So you can always go from this to this. If you want to go from this to this nu, it is the same as if you are first going from this to this via some transformation, from this to this tau transformation, and then coming to back. So this is what it means. So basically, it's a sort of diagrammatics of how we can have these orthogonal transformations or unitary transformations via some matrix transformations by which we translate one space into another space, invariant space. Or components remain same, but the space may be different. Or the space remains same, but some matrix transformations, the components translate from one space to another space. And you can map from one to another by inverse transformation or adjoint transformations, which is called active or passive transformations. So this is the simplest way. So for homogeneous spaces, the simplest way can be how we can go from a given transformation, how we can via one or more transformations, how we can arrive at two transformations via other transformations in space also. For homogeneous spaces. For heterogeneous spaces, we have the thing of dimensions you have to specify. So this is another way of, this is the mnemonics or diagrammatics for the same of Arrhenius. So it needs a bit of more, what I should say, facility or exercise of going through this, then we can enjoy it probably. Because it's later helpful how these transformations are there. In quantum mechanics, unitary transformations are very much used, and they just operate through matrix transformations, which are taken as operators, and how can relate one space to the another space, to the transformations from one space to the another space. So that becomes important as a tool also. So what are the philosophical implications? Will come by and by. What does it mean that some transformations they are invariant? Under certain transformations, things remain invariant, or they are symmetric, or under inverse transformations, or reverse transformations, things should come where you started, back where you started, you come back where you started. So what do you mean by them? So we'll come to those questions in future. Thanks.